So I just did a review of the size principle, if you watch that, and that clearly implies that inside of any given muscle, this could be the biceps muscle, for example, there's a combination of different muscle fiber types. So within any muscle, it really doesn't matter the type of muscle that it is, there are slower twitch fibers, there are different types of fast twitch fibers, type 2A, type 2X. And the size principle kind of tells us the order in which those fiber types are recruited. It also just tells us how more muscle fibers within a muscle fiber are recruited when we want to produce more force. But what I want to do right now is really talk about the more advanced differences between type 1, type 2A, and type 2X. I did some of that already earlier on. That was what I would consider more so the more basic components of the differences between fiber types. And now I want to get into some of the more, let's say, newer areas of research regarding these different fiber types and why they're different from each other. This is the stuff that you've seen before, but I'm still going to use it to build into the more advanced conversation. Okay, so in this table we have type 1, the slow twitch muscle fibers, type 2A, fast, moderate fast twitch fibers, and then type 2X, which are the fastest fast twitch fiber. Now, the most important thing in this table for our conversation right now is what's called the ATPase activity. That just basically means the rate at which any one of these fibers consumes ATP. Okay? What that really translates into is what's the myosin head cycling frequency of that fiber. Okay? If the myosin heads cycle more frequently, they consume more ATP because each time that they cycle, they consume a molecule of ATP. So what you'll see is that the ATPase activity of the slower twitch muscle fibers, type 1 muscle fibers, is slow. I mean low, not slow. So slow twitch type 1 muscle fibers, they have a low ATPase activity. Basically, that means they consume ATP at a low rate because their myosin heads cycle at the lowest frequency. Now, we move into type 2A. We see that the type 2A fibers have a higher ATPase activity, and that means that their myosin heads cycle at a higher frequency than like type 1, for example. But then we look at type 2X, which are the fastest twitch fibers, and we see that their ATPase activity is the highest. That means that the type 2X fibers consume the most ATP. And what that really means is that their myosin heads cycle at the highest frequency, cycling per second, for example. How many times do they cycle per second? And thus they consume the most ATP. Okay, so we can determine by looking at the ATPase activity which fiber has the myosin heads with the highest cycling frequency. But what can we extrapolate from that? The next thing that we can look at is we can look at the Vmax, which also really means the speed of shortening. What's the shortening velocity? Well, slower twitch fibers have a low shortening velocity, right? They shorten very slowly, and that's because, again, their myosin heads cycle at a relatively slow rate. They consume low quantities of ATP, and thus they don't shorten very fast. Okay? Then we move to type 2A, and they have a pretty high shortening velocity, right? They can shorten decently fast. And that's because, again, we look at the ATPase activity and we see that within type 2A fibers, their ATPase activity is relatively high, meaning that their myosin heads cycle at a decently high frequency. And if they cycle at high frequency, then they must be able to shorten fast, right? The speed of shortening is pretty high. And then we look at type 2X. And of course, they have the highest speed of shortening, the highest shortening velocities. They shorten the fastest. Why do they shorten the fastest? Because their myosin heads have the highest cycling frequency. If any given muscle fiber has myosin heads that cycle at higher frequencies, they're going to shorten faster because actin will be pulled towards the M line, of course, at a faster rate. So that's the first thing that I would point out about this table. The next thing that's relatively easy to take out of this is the resistance to fatigue. Okay, well, we think that we're going to talk about this actually in a little bit in the next, right at the beginning of the next module. But fatigue, we think, comes from ATP being consumed uh, at a greater rate than it's being produced. Okay, well, slow twitch type 1 muscle fibers must be have a pretty high resistance to fatigue, right? They don't fatigue very easily, and that's because, again, they don't actually, if you look down here, they don't consume much ATP, right? Their myosin heads don't cycle at high frequencies. By consequence, they don't shorten very quickly. But the benefit to that is they're incredibly resistant to fatigue. They really probably don't ever, especially the slowest of the slow twitch fibers, and I said this in the past, I know, but the slowest of the slow twitch fibers really don't ever probably reach a point where their ATP consumption is higher than their supply. Now, type 2A fibers, we would say, are somewhere between high to moderate resistance to fatigue. And again, we can always tie this back to the ATPase activity. The ATPase activity within these type 2A fibers, these kind of moderate fast twitch fibers, is decently high, right? The myosin heads can cycle at a relatively high frequency, thus they can shorten at a relatively high frequency. And at their upper limits, meaning that they're, really put into a state of tetanus, and also frequently being put into a state of tetanus, so being asked to contract very forcefully and very frequently, they can reach a point where their ATP demands are higher than their supply of ATP, and thus they can fatigue. But they are still considered relatively fatigue resistant because that situation doesn't happen all that often. I mean, it does during exercise, of course, but it's you really have to work these fibers to get them to fatigue. All right, next, if we look at type 2X fibers, their resistance to fatigue is incredibly low. Why is their resistance to fatigue incredibly low? Again, we can tie this to their ATPase activity, right? They consume huge quantities of ATP because their myosin heads cycle at a very high frequency, thus they shorten at a high frequency. But because of the fact that they consume so much ATP over a short period of time, they often are put into situations where their ATP demand is higher than their supply, and thus they fatigue. Now we can continue on and look at the more basic components, the remaining basic components of this graph. The predominant energy system, okay? Slow twitch fibers, this says aerobic, but I would say that they are heavily reliant on what we would call slow metabolism. They have a very high quantity of mitochondria inside of them. They produce lots of ATP through slow glycolysis and beta oxidation, which are both slow means of producing ATP with fatty acids and carbohydrates. But that is fine because, again, their ATPase activity is quite low, right? They don't have a very high ATP demand, so the supply of ATP for these fibers can very easily be met through slow metabolism, through slow glycolysis and the breakdown of fatty acids, beta oxidation. We look at type 2A fibers, and they use a combination of slow and fast metabolism. These are the fibers that I was really talking about when I was going through metabolism at the beginning of the class, from a slower intensity to a higher intensity, a lower ATP demand to a higher ATP demand. These fibers will use a combination of both slow and fast metabolism to meet their ATP demands dependent upon what the fiber is being asked to do. Is it being asked to contract very forcefully and very frequently? Then it's going to use a strong combination of fast and slow glycolysis, fast and slow metabolism. Is it not being asked to contract very forcefully and frequently? Then it's going to rely more heavily on slow metabolism. And as you well know, the fastest twitch fibers, type 2X fibers, rely heavily, almost exclusively, on fast metabolism, right? Why? Because they have an incredibly high ATPase activity, a very high ATP demand, myosin head cycling frequency, and thus they rely on an energy system that can produce ATP at very rapid rates to assist in meeting their ATP demand. So you'll see that the fastest twitch fibers don't have very many mitochondria, because they simply don't bother with utilizing a lot of slow metabolism. That doesn't mean, though, that these fibers are limited in the amount of oxygen that they receive. This goes back to the metabolism theories. Okay, yes, as the fiber becomes faster and faster twitch, it has less mitochondria inside. But the real conversation is, just because the fiber has less mitochondria, does that really mean it ever becomes limited in the amount of oxygen that it can receive? Do all fibers just have a proportionate number of blood vessels per the number of mitochondria that they have? Excuse me. Why a fiber transitions to utilizing fast metabolism may have very little to do or nothing to do with the fact that it's not receiving enough oxygen for its mitochondria. These fibers, fast twitch fibers, especially type IIx fibers, may just be designed, through the lactate dehydrogenase and enzyme isoform that they have, or lack of NADH and pyruvate transporters, to just simply run fast glycolysis quite frequently, regardless of how much oxygen they're receiving. So yes, anatomically, it is true that as a muscle fiber becomes faster and faster twitch, it has less and less mitochondria. But just to reemphasize conversations from the past that we've had, the number of mitochondria that it has, doesn't necessarily indicate why that fiber is more reliant on a particular type of metabolism. Maybe it does, maybe it doesn't. And the last thing here is specific tension. That means per area, how much force can the fiber produce? Okay. Slower twitch fibers, if we know that, for example, as a fiber becomes faster and faster twitch, it becomes bigger. Right? We discussed that with the size principle. Okay. As slow twitch fibers are the smallest, and as the fiber becomes faster twitch, anatomically the fiber becomes larger. Okay. But if we were to take these three fiber types and cut them to the same exact size, or make them the same exact size, or just what this really does is it just looks at how much force can be produced in that fiber per area, right? If we're looking at the exact same amount of area in each one of these fibers, how much force can it produce? What we see is that both type IIx and type IIa have about the same specific force or specific tension. What this really means is per area, these two fibers can actually produce the same amount of force, which means they have about the same amount of myosin and actin inside. There's really not, yes, if you look at the whole fiber, type IIx fibers can produce more force than type IIa fibers, but that's really just because they're bigger than type IIa. If you looked at the same amount of area within a type IIx fiber versus the type IIa fiber, they can really produce about the same amount of force. And then compared to type 1 fibers, they can produce the least what's called specific tension or specific force. Like per area, type 1 muscle fibers, the slow twitch fibers, produce less force than type 2a or type IIx. That actually means that per area, type 1 fibers have less actin and myosin. So in theory, if you had a type IIx fiber, a type 2a fiber, and a type 1 muscle fiber that were all the exact same size, right? This wouldn't happen, but if they were all the exact same size, the type IIx fiber and the type 2a fiber would produce the same amount of force approximately. The type 2x would actually produce a little bit more, but they're very similar to one another. And the type 1 muscle fiber would produce a lot less force than the type 2a or the type IIx. And again, this is if they were all the exact same size. So those are the basic, well-established differences between type 1, type 2a, and type IIx muscle fibers. Okay, but there are also some much more advanced differences that we know about with regard to these different fiber types, and exactly what they do and how they do it is not fully understood, and that's what I want to talk about with you right now. Okay, so the big part of skeletal muscle physiology, advanced skeletal muscle physiology, is understanding the role of these light chains within the myosin proteins. Okay, so a myosin protein has two heavy chains, which coil around each other in a double helix and then split to each form one head. But then within each head, there are two light chains. So each myosin protein has a total of 6 proteins within it. And this is true for the myosin heads that exist within type 1, type 2A, and type 2X muscle fibers. They all have regulatory light chains within their myosin heads. We know this. Yeah. And what we know about these regulatory light chains is that they can actually be phosphorylated. And these regulatory light chains can be phosphorylated within all of the different fiber types. First of all, how do they get phosphorylated, and what does that phosphorylation actually do? How they get phosphorylated is relatively simple. When you ask a muscle fiber to contract, regardless of the fiber type, you're going to see calcium build inside of that fiber for reasons that are well established now that we've discussed with excitation-contraction coupling. And what calcium will do is calcium will combine, you've seen this before, with calmodulin. Calcium can combine with calmodulin, and then what calcium calmodulin can do inside of skeletal muscle fibers is it can also activate something known as MLCK, which stands for myosin light chain kinase. Myosin light chain kinase is a specific type of kinase that phosphorylates, kinase always phosphorylates things, but it phosphorylates the myosin light chains. Okay. Myosin light chain kinase, which is activated by calcium calmodulin, the complex, will phosphorylate these light chains within skeletal muscle cells. And again, this same thing happens within all of the different muscle fiber types. But there are different isoforms of the light chains within the different skeletal muscle fiber types. So first of all, let me just tell you what we think kind of the basic idea of what happens when these myosin heads light chains get phosphorylated, and then kind of delve into the differences between the fiber types themselves. So before we get started here, let me tell you what sort of started this whole, all of this theorizing and all these studies that are revolving around phosphorylation of the light chains in skeletal muscle fibers. All right, so if you you can do this with a human being, you can do this with a frog muscle. It doesn't matter. If you hook a muscle fiber up to a stimulator or a collection of muscle fibers, some muscle tissue, and you send it, you give it 1 hertz, like 1 action potential, what you'll see is twitch. You will not see, that's a kind of a bad of a twitch, but you will not see maximal force production. Of course, you will not see tetanus within that muscle fiber or those muscle fibers that you sent an action potential to, just 1 action potential. From all our prior conversations and what we've already discussed in this course, I hope that makes a good amount of sense. Now, you let the muscle fiber rest, or fibers rest for a few seconds, a second or two, and then you hit it with another action potential, just 1 action potential, 1 hertz. And what you'll see is another twitch, but with this twitch, more force will be produced than during the first twitch. Now, this has nothing to do with summation. It can't, because summation happens when successive action potentials are sent to the muscle fiber fast enough, or frequently enough, excuse me, so that calcium levels are never allowed to completely deplete inside of the fiber before more calcium is released. What you're allowing to happen here is complete relaxation. Okay? You let the fibers completely relax, and then you hit them with another action potential. And with that second action potential, more force is produced during the second twitch than during the first twitch. You'll see this with any. Some people argue you see this even with tetanus too, but certainly the biggest times that you see this is with anything that's sub-tetanus. So if the frequency of action potentials to the muscle fiber is below the frequency of action potentials that causes tetanus. So if you hit it with 8 action potentials per second, the muscle fiber, right, you're going to get some summation there in force. Okay, then you take a break. You let the muscle fibers completely relax, and then you hit it with 8 action potentials again in a second, 8 hertz. The second 8 action potentials that you send to the muscle fiber, the summation will be greater the second time than the first time. You'll get more force the second time than the first time. The question is really, what's not as clear is, does that happen in actual frequencies that elicit tetanus. Studies are real divided on that, but nobody disagrees with with a subtetanus stimulus. You're going to see what's called potentiation. That's what this is. This is muscle potentiation. Certainly, as long as the stimulus to the muscle fiber is below tetanus, let's just stick with a twitch because that's easy. If you send a muscle fiber one action potential, right, it'll produce a twitch. You take a break, you send it another action potential, it'll produce another twitch, but it'll produce more force the second time around. Nobody debates this. But the question is why? And this observation, as I said a couple minutes ago, is what started a lot of this research. Okay, so most people would agree that this is probably coming from phosphorylation of the myosin head light chains. So during the first contraction, okay, the first twitch, what happened inside of the fiber, right? Calcium was released from the sarcoplasmic reticulum and it bound to some troponin and allowed some myosin and actin to interact, and that's what caused the contraction and the force. But also some of that calcium bound with calmodulin, and calcium calmodulin activated myosin light chain kinase. And what myosin light chain kinase was able to do is it went over and it phosphorylated the myosin light chains. Certainly not all of them, but some of them. And that phosphorylation of the light chains is what a huge majority of people agree is what allows for when that muscle fiber is hit with the second twitch, hit with the second action potential after total relaxation, to allow that muscle fiber to produce more force during the second twitch. And beyond that is where things get really messy and there's not a lot of agreement. There's so many different theories revolving around what phosphorylation of the light chain actually causes. I'm going to give you the most common ones. There's by no means universal agreement here on which of these is the best. It's constantly changing. So let me just tell you some of them. All right. So first of all, it's possible and looks to be fairly evident that in a non-phosphorylated situation, so when the myosin light chains are not phosphorylated, it looks like the myosin heads are much more parallel to actin. You see where it says off position here? These myosin heads, you can see they're very much so parallel to the actin filament. Okay, when they're parallel to the actin filament, what's implied is that the myosin heads, when they're parallel to actin, have less basically of a likelihood or a tendency to actually bind actin. All right, so what happens when you phosphorylate the light chains? You see where it goes to the on position here. The myosin heads become much more perpendicular to actin. They go from being parallel when they're not phosphorylated, they go from being parallel to actin when they're not phosphorylated to being perpendicular to actin when they are phosphorylated. And when they're perpendicular, this theory would tell us that the myosin heads have a much greater likelihood, statistical likelihood, of interacting with actin. So make the myosin heads perpendicular to actin, and the probability that the myosin heads will actually bind with actin is significantly increased. All right, so let's talk about how this then would relate to the two different twitches. Okay? So if this theory is correct, okay, you hit the muscle fiber with the first action potential, the muscle fiber produces a twitch. Okay? During that twitch, right, calcium was released from the muscle fiber. It allowed for myosin and actin to interact, but even more importantly for this conversation, calcium that was released, some of it bound with calmodulin, activated myosin light chain kinase, and myosin light chain kinase phosphorylated the myosin head light chains. And the myosin heads, they went from a more parallel position to actin to a more perpendicular position to actin. And this phosphorylation appears to last for a while. Okay? It doesn't, it's not reduced as quickly as the fact, like just calcium going back into the sarcoplasmic reticulum. You actually need phosphatases to come along and remove these phosphates. So these myosin heads, these myosin head light chains, they stay phosphorylated for a while. So this orientation of the myosin heads now being perpendicular to actin stays like this for a while. Okay, so now you wait a second or two and you hit it with another twitch. You hit it with another action potential so that another twitch will occur. Okay, so you hit the fiber with another action potential, and then the action potential results in a more forceful twitch the second time around. More force is produced with the second twitch than with the first twitch. And why would that be in this theory? Well, that would be because of the fact that the myosin heads are now, the myosin heads within this muscle fiber are now more perpendicular to actin. And because of this, the probability that myosin and actin will interact is increased than in the first twitch. Okay? And by consequence, during the second twitch, more myosin and actin will actually interact and more force will be produced during the second twitch. We will call this theory number 1. Okay, this is theory number 1. It's the myosin heads moving from parallel to perpendicular theory as to what causes muscle potentiation. So what about theory number 2? Theory number 2 is directly related to theory number 1. Okay? What we know now is definitely there are proteins that actually attach the myosin filaments and actin filaments to each other. Okay? I'm not saying that the myosin heads are always attached to actin. Right? That's by no means what I'm implying here. I'm saying that there are these structural proteins like myosin binding protein C and other proteins that actually attach the myosin filaments and actin filaments. Go back 20 years and nobody really knew this or thought that this was true. They thought that these two protein filaments were really kind of independent from one another until contraction began. Okay, so you have to recognize that, first of all, that there may be proteins that are actually attaching the myosin and actin filaments to each other at all times. Now, what influence might that have? Okay, so you hit the muscle fiber with the first action potential, you cause a twitch. During that first twitch, myosin light chain kinase, due to an increase in calcium inside of the fiber, phosphorylates the myosin light chains. And it looks like phosphorylation of these myosin light chains may actually cause troponin within the actin filament, on the actin filament, to become more sensitive to calcium. So yes, I'm saying that phosphorylation of the light chains within the myosin heads is actually causing a change within troponin that exists on actin. Okay? There's a lot of evidence pointing to that as being a possibility. Some people still believe that the troponin, basically proteins, can be phosphorylated themselves too, which may also be a possibility, but there's I would say good evidence that phosphorylation of the light chains actually changes components, structural components of actin. Basically, what would happen here is the myosin light chains would be phosphorylated, and then there would be, conformational shifts in different proteins, and those conformational shifts would ultimately translate into troponin being more sensitive to calcium. Okay, and this would last for a while. So when you hit that muscle fiber with another action potential and you cause another twitch, right, you would see more force with the second twitch than the first twitch. And this would be, in this example, because with the second twitch, because of the myosin light chains being phosphorylated, right, during the first twitch. With the second twitch, now troponin is more sensitive to calcium, and troponin will bind more calcium, and thus more tropomyosin will unwind off of G-actin, off of the actin F-actin strands, and that will allow for more myosin and actin to interact, and more force will be produced during the second twitch than the first twitch due to increased troponin calcium sensitivity. This second theory and the first theory kind of go hand in hand. A lot of people that believe the first and the second think kind of both of these things happen. They think that when the myosin light chains are phosphorylated, that the myosin heads go from a more parallel to perpendicular position, and that troponin increases its calcium sensitivity. And those two things would translate, of course, into much more force being produced with a second twitch than a first twitch, because of the fact that the myosin heads are now more perpendicular to actin, and there's more probability that they'll bind to actin, and because of the fact that the troponin has a greater calcium sensitivity, now also more tropomyosin will unwind off of actin, allowing more myosin and actin to interact. So let's move on to theory number 3. Theory number 3 is relatively easy. This just simply says that when the myosin heads get phosphorylated by myosin light chain kinase, it actually allows the myosin heads to produce more force when they interact with actin. It's as simple as that. So any of the myosin heads that are phosphorylated, the myosin light chains, any of the myosin heads that have their myosin light chains phosphorylated, those myosin heads, their basically cycling kinetics are manipulated, and now those myosin heads, when they interact with 1G-actin, each one of those myosin heads is actually able to produce more force than when those myosin heads weren't phosphorylated. So in this theory, you really wouldn't get you wouldn't get a change in the number of myosin heads that are actually bound to actin. So you would still see during the first twitch, less force would be produced, and during the second twitch, more force would be produced. But in this theory, the number of myosin heads actually bound to actin wouldn't change. What would change is the fact that the myosin heads that are bound to actin during the second twitch are able to produce more force than they were during the first twitch, because now they've been phosphorylated. This is really probably the simplest theory. This is one of the first ones that existed. And it very well may still be accurate. There are lots of people that think it is. But at the moment, theory 1 and 2 have become, let's just say, I don't know, you could call them more trendy at the moment than theory 3. All of these are very, very hard, almost, with the technology we currently have, impossible to really prove one way or another. That will change, of course, with time, but we're talking at such a micro level here. It's impossible to make definitive statements about any of these theories. Now, for theory number 4, which doesn't really deal as much with potentiation, but will become important for our conversations. If the myosin light chains are phosphorylated, some people believe that this allows the myosin heads to actually cycle faster. Okay, that's important. I'm not saying cycle more frequently. I'm saying phosphorylation of the myosin head light chains, the regulatory light chains, actually enables the myosin heads, when they do cycle, to cycle faster. Basically, their cycling velocity increases. I'm not saying it changes their frequency of cycling. Maybe that happens too. It's possible. But what I'm saying is there are scientists who also believe that phosphorylation of the light chains actually allows these myosin heads to cycle at a higher velocity. Okay. It's important to know that most people believe that the actual cycling velocity of the myosin heads is very similar between type 1, type 2a, and type 2x. okay, like the cycling velocity. What's different is the frequency, and that's what changes what allows, for example, faster twitch fibers to shorten at faster velocities. It's the fact that their myosin heads cycle more frequently. Like, let's say that the myosin heads cycle 150 times over the a given amount of time, versus in a slower twitch fiber they only cycle 50 times over that same period of time. So it's not actually that the myosin heads within the faster twitch fibers, when the head cycles itself, it's not that head has a faster velocity. It doesn't cycle faster. It cycles more frequently. Now, this theory would say in some muscle fibers, and this is going to get to my point quite quickly, in some muscle fibers, when the light chains are phosphorylated, it does actually allow the myosin heads to cycle at higher velocities. So if this is a fast twitch muscle fiber, the myosin heads would still have a cycling frequency of 150 times over the course of 3 seconds, I don't know, 5 seconds, 1 second, whatever you want it to be. But now when that myosin head gets phosphorylated, its cycling frequency stays the same of 150. But now, with each cycle, the velocity at which the head actually cycles increases. So the frequency of cycling is still 150, but with each cycle, the head is actually moving at a higher velocity. This will make more sense a little bit later on. All right, so what's important about all these different theories? What's important about all these different theories is we know that there are different myosin light chains that exist in different muscle fibers. Type 1 muscle fibers have a specific myosin light chain isoform. Type 2A do. Type IIx have a specific isoform. So these different theories would happen to different degrees inside of different muscle fiber types. Now, that will only make sense if I give you a practical example of this, which I'm about to do with the discussion of what's called power. To continue talking about that, I want to go back to this idea of specific force. Specific force, again, is the amount of force that a muscle fiber can produce per area. Okay, so let's just say this hypothetical situation where we have the same sized type 1, type 2A, and type 2X muscle fiber. They're all exactly the same size. What you would see is at the exact same size, the type 1 muscle fiber would produce much less force than the type 2A or type 2X fiber, and that's because it has less myosin and actin per area. Okay? Now, the type 2A and type 2X fiber, pretty much, if they were the exact same size, would produce very close to the same amount of force. The type 2X looks like can produce a little bit more than the type 2A, but they're very, very similar from one another. But then, when we look at power, they're vastly different than each other. So what is power? So power is how much force a fiber can produce, but over time. Okay, it's very specific. Power is an incredibly specific term in exercise physiology. So it seems kind of abstract, but it's actually really easy to measure. Okay, so power, without getting into all of like the relative power and all this stuff, which can make it really confusing. Pretend that you have two people that are identical. That you clone somebody. So it's a clone of yourself, right? That person has the exact same amount of muscle as you have, the exact same amount of fat as you have, is exactly as tall as you are. Okay, they're the exact same person as you. The only difference is somehow genetically you've given that person all type 2A muscle fibers and you have all type 2X muscle fibers. Otherwise, you're exactly the same. You both get on a cycloergometer, a bike, and pedal against 3 pounds of resistance. Okay? And you do 25 revolutions. Okay? You do 25 revolutions. With each revolution, you would go approximately 6 meters. So you would both go a total distance of 150 meters. I'm going to change pounds to kilograms, okay? So you're both pedaling against 3 kilograms, because this is technically the way that it's usually done. 3 kilograms is much more than, it's more than double what 3 pounds is. All right, but nothing has changed. You both have gone 25, you both have done 25 revolutions on a bike against 3 kilograms of resistance. So you both went 150 meters and went 150 meters with 3 kilograms of resistance. So what you would do is you take 150 meters and you would times that by 3 kilograms. And we would say that that is 450 kilogram meters. That is what we will say is the amount of force that you have produced. In exercise physiology, this is actually called work, but we'll say that it's, you can also call power work over time, but I think it's easier to think about it as force. Just stay focused on not the terminology and more so what's actually being shown here, okay? You both went 150 meters on the bike against 3 kilograms of resistance. So 150 meters times 3 kilograms of resistance is 450 kilogram meters. You both performed the exact same amount of work or produced the exact same amount of force. All right, but now let's say that you do this again. You do the exact same thing, and this time you both try to complete this as fast as you possibly can. Okay? You both try to complete 25 revolutions against 3 kilograms of resistance as quickly as humanly possible, both of you. You have mostly type IIx muscle fibers and your clone has mostly type IIa muscle fibers. Let's just make something up. You complete this in 12 seconds and your clone completes this in 15 seconds. You completed it much faster than your clone did. Now we can actually look at power, because power is force or work over time. So in this case, you both still produced the same amount of force. You both still produced 450 kilogram meters because you both still did 25 revolutions against 3 kilograms of resistance. But it was timed this time. You completed it in 12 seconds and your clone completed it in 15 seconds. So here's what you would do. You would take 450 kilogram meters and you did this over 12 seconds. That equals 37.5 kilogram meters per second. Okay? That is your power. 37.5 kilogram meters per second. Now, let's look at your clone. They also went 450 kilogram meters, right? That's what they performed, but it took them 15 seconds to complete it. That equals 30 kilogram meters per second. Which one of you is more powerful? You are, right? You are the one with mostly type IIx fibers, and your clone has mostly type IIa fibers. You were able to produce more force over time than your clone was. You produced 37.5 kilogram meters a second, while your clone produced 30 kilogram meters per second. That is what this is depicting. Type IIx muscle fibers are much more powerful than type IIa muscle fibers are. They can produce about double the amount of force. So my example didn't do justification to this, but they can produce about double the amount of force over time than compared to type IIa muscle fibers. This is why people who play power sports, forward in soccer or basketball or components of hockey or basically every sport to some degree, linemen, running backs, most volleyball, most sports have big power components to them. You want people to produce lots of force over short periods of time. That's what sprinting is. And type IIx fibers by far produce the most amount of force over time. And that looks relatively confusing when you look at the graph above. right? Because if you look at the muscle fiber type per area, okay, Type IIx and Type IIa actually produce about the same amount of force, but their powers are vastly different. They have about the same amount of myosin and actin per area. So in terms of the maximal amount of force they can produce per area, they're about the same. But when you look at the amount of force they can produce over time, they're vastly different. So the question, of course, is what internally is different about Type IIx versus Type IIa muscle fibers? We know that Type IIx muscle fibers, the myosin heads, have higher cycling frequency than Type IIa do, so they can shorten faster. But why does that mean that they can produce more force over time? Just because they can shorten faster, that can't be, the entirety of the answer. And to better understand this, we can compare these two fiber types with what's called the force-velocity relationship. And then we can tie back in these regulatory light chains and other things that we know about faster twitch fibers. So there's a fairly basic principle, which is the force-velocity relationship. Okay, as a muscle fiber shortens faster, as its shortening velocity increases, it always produces less force. So you can see here, pick any one of these fibers here. It doesn't ultimately matter at all. If you look here, as velocity increases, shortening velocity, the amount of force that is being produced progressively decreases, right? So as the fiber shortens faster, it produces less force. I always do this. Just think of a squat, right? If you want to produce the most amount of force possible, like if you want to lift something really heavy, you can't do it quickly, right? You have to lift that object very, very slowly. And that's because when muscle fibers shorten slowly, they can produce more force, right? As shortening velocity decreases, more force can be produced. And the basic principle of this is, well, if a muscle fiber shortens really quickly, then myosin and actin are moving past one another at a rapid rate, and less myosin and actin can interact, and thus less force can be produced, because force is proportional to the amount of myosin and actin that interact with each other. Now, if myosin and actin move past each other very, very slowly, like a slow shortening velocity, then they have more time to interact and more force can be produced. That's the basic physiology of the force-velocity relationship. You've all heard this before. And you've seen some of this before too, but I didn't really, in the past, in previous courses, tell you the entirety of what we know about this. All right, if, let's say here we have Type IIx, and in blue is not slow, blue is Type IIa. All right, watch what happens here. In Type IIx and in Type IIa, as they increase their shortening velocity, both of them produce less force. There's no fiber type that is immune to this concept. Any fiber type that shortens faster, the faster it shortens, the less force it will produce. But at a given velocity, which of the fiber types is always producing more force? The Type IIx. The Type IIx at any given velocity always is going to produce more force than the Type IIa. They're both shortening at the exact same velocity, okay? Right here, for example. But at this velocity, the Type IIa fiber is producing a lot less force. At this velocity here, the Type IIa fiber is producing a decent amount less force than the Type IIa, and it becomes even more dramatic as you move to higher velocities. Now, how could it be that both fibers are shortening at the exact same velocity, but one of them is producing more force? And the answer to this is incredibly complicated, and nobody knows the answer for sure. The simplest explanation given for years was, well, the myosin heads have, the myosin heads within Type IIx fibers cycle at a higher frequency, than the type 2A fibers do. So thus, over a given amount of time within that type 2X fiber, more myosin and actin will interact over time than compared to the type 2A fiber. So because the type 2X fibers, myosin heads, cycle at higher frequency than the type 2A fibers, over a period of time, more myosin and actin interact within the type 2X fiber than within the type 2A fiber at that given velocity. Thus, the type 2X fiber produces more force than the type 2A fiber. That almost certainly doesn't account for everything, or maybe any of it. What most likely accounts for it are differences in the regulatory light chains within the type 2X versus the type 2A fibers, as well as what's called myosin binding protein C, and some of these other proteins that we know that exist within different fiber types. Okay, let's just say that the type 2X fiber, we know this, does have a different myosin head regulatory light chains compared to the type 2A. Perhaps the type 2X fibers, the myosin heads are put into a more favorable position than the type 2A fibers, or more of them are. And I mean, you could just play around with this idea and say, well, if type 2X fibers have regulatory light chains when they're phosphorylated that put the, let's say, myosin heads into a more perpendicular position compared to actin, compared to the type 2A fibers, then at this exact same velocity, right, the type 2X fiber and the type 2A fiber are shortening at the exact same velocity, but the regulatory light chains are different in the type 2X versus the type 2A, and thus the myosin heads within the type 2X fiber are in a more perpendicular position to actin than the type 2A fibers are. Then at that exact same velocity, more myosin and actin within the type 2X fiber would be interacting compared to the type 2A fiber. And thus the type 2X fiber, because of the differences in the regulatory light chain, would actually be producing more force than the type 2A fiber. Additionally, perhaps the calcium sensitivity is increased to a greater degree in the type 2X fiber compared to the type 2A fiber because of the phosphorylation of the regulatory light chains. That would mean at that same velocity, there'd be again, greater calcium sensitivity within the type 2X versus the type 2A, and that would enable more myosin and actin to interact within the type 2X versus the type 2A. That would account for theory 1 and 2, but theory 3 could also be equally as true, right? So both muscle fiber types are shortening at the exact same velocity. And in theory 3, that we talked about earlier on, if the myosin light chains are phosphorylated, then the myosin light chains, the myosin heads with their myosin light chains that are phosphorylated, those myosin heads, when they interact with actin, can actually produce more force. So let's just, again, these are type 2X, these are type 2A, okay? Type 2X is producing much more force than type 2A at this exact same velocity. And if theory 3 comes into play here, what would account for this is, yes, both of the muscle fibers are shortening at the exact same velocities, but the type 2X has different regulatory light chains than the type 2A. And each myosin head within type 2X that interacts with actin is able to produce more force than each myosin head that interacts with actin in type 2A. So because of phosphorylation of the light chains within the myosin heads being different between the type 2X and the type 2A, each myosin head that interacts with actin is able to produce more force within the type 2X fiber than the type 2A fiber, and that would account for why more force is being produced at any given velocity. So the overarching point is differences in the myosin light chains, the regulatory light chains within the myosin heads, right? Differences between fiber types, type 2X versus type 2A, probably plays a very big role in why type 2X fibers are able to produce more force at a given velocity than type 2A. And also, just the sheer fact that the myosin heads within type 2X can cycle more frequently than type 2A that probably also, plays some role as well to some degree. Again, mathematically, just over time, if type 2x fibers have myosin heads that can cycle at a higher frequency than type 2a, more myosin and actin should interact over that time within the type 2x versus the type 2a. So that would probably help account for some increased force production at a given velocity too. So what I went over with you does answer this question, but it doesn't actually apply to real life. Like if at the same velocity, a type 2x fiber can produce more force than a type 2a fibers for the reasons that we discussed, then of course over time a type 2x fiber is going to be able to produce more force than a type 2a fiber can. Again, if their shortening velocities are identical, and type 2x fibers, at that same shortening velocity as type 2a fibers are producing more force, then over the period of time, the type 2x fibers are going to produce more force than the type 2a fibers will. And that is, by definition, what power is. How much force can be produced over time. And what I've tried to show you here is probably what accounts for this. There's lots of interesting intracellular mechanisms within different fiber types that vary, that probably account for these huge differences in power that exist between fiber types. So in practical real-world terms, the example that I just gave you of being able to produce more force at the same velocity doesn't really apply to our example of two clones racing against each other. That's great if the person with mostly type 2x can produce more force at a given velocity than somebody with mostly type 2a. That would be applicable to like weightlifting, for example. Okay, let me explain. You've got somebody with mostly type 2x and then another person with mostly type 2a. Okay, their biceps muscles would be shortening at the exact same velocity as they're producing elbow flexion. They're both performing a biceps curl, but the person with mostly type 2x can produce more force at that exact same velocity than the person with mostly type 2a. Okay? So what you would see is the person with mostly type 2x, while they're performing a biceps curl, elbow flexion, at the exact same velocity as somebody else with mostly type 2a, they might be able to lift 25 pounds in their hand, while the person with mostly type 2a would only be able to lift 15. Again, their elbows are, performing flexion at the exact same velocity. Their biceps muscles are shortening at the same velocity, but the person with mostly type 2x can produce more force than the person with mostly type 2a. So while their elbows are shortening at the exact same velocity, performing a biceps curl, the person with type 2x can actually lift more weight than the person with mostly type 2a. But again, this example doesn't really help us understand how two clones of one another, why somebody with mostly type 2x would be able to finish a race faster than somebody with mostly type 2a, because that all deals with velocity and they're moving at the same velocity. So the fact that somebody with mostly type 2x during a race can move at the same velocity as somebody with mostly type 2a and then produce more force doesn't actually help us understand how they could finish the race faster. Because in that example, they'd both be moving at the same velocity. Their muscles would be shortening at the same velocity. So by consequence, they would both theoretically finish the race at the same time. Who cares if the person with the type 2x fibers is producing more force while their fibers are shortening at that same velocity as somebody with the type 2a? They're still shortening at the same velocity, so what difference does it make? For this to make sense of my sort of clone example, you've got two clones running against each other, right? You're running against your clone, I guess. They're the same height as you. They're the same weight as you. They have the same amount of fat. They have the same amount of muscle. Right. The only difference is you have mostly type 2x and they have mostly type 2a. So to really understand why type 2x being more powerful would enable you to finish the race faster, you have to flip this relationship on its head and look at it the opposite way. Okay, since both of you weigh the exact same weight, you both have to produce the same amount of force to move your bodies. You both weigh 150 pounds. Okay? So you both weigh 150 pounds, so you both have to produce enough force to move 150 pounds. So you would both be producing the exact same amount of weight to move your body, and now you have to come over and you say, okay, well, if you're both moving the exact same amount of weight to move your body, while you both produce the same amount of weight, whose muscle fibers are going to be shortening at a faster or higher velocity? Over here, again, would be type 2x. Over here would be type 2a. Okay? If you're both producing the exact same amount of force to move a 150-pound human being, at that exact same amount of force to move 150 pounds, the person with mostly type 2x, you would be able to shorten your muscle fibers at a faster velocity than the person with type 2a, your clone. This is what's important about racing, right? If this relationship, both have to be true. Like the reverse of what we just went through has to be true too. Like if at the same velocity, a person with type 2, mostly type 2x fibers can produce more force than somebody with type 2a fibers, then the opposite must be true as well. At the same exact force production, the person with mostly type 2x fibers is going to be able to shorten their muscle fibers at a higher velocity than somebody with mostly type 2a. And you versus your clone, this is what's most important about you finishing the race before your clone does. Now, there's a bit of a problem to grapple with here. Okay? If you're both producing the exact same amount of force, right, isn't force proportional to the amount of myosin and actin that are interacting? So if you're both producing the exact same amount of force, right, shouldn't the number of myosin interacting within the person with mostly type 2x fibers be the same as the person with mostly type 2a fibers? Because they're both producing the same amount of force, and they both have the exact same amount of muscle because they're clones. And shortening velocity is really all about the rate at which actin is pulled towards the M line, which is going to be dictated by, the cycling frequency of the kind of the myosin heads, and thus the number of myosin heads that are bound to actin pulling it towards the M line. My point is, if at this exact same force production, somebody with mostly type 2a and mostly type 2x, if both of their muscle fibers are producing approximately the same amount of force to move their bodies, then how could it be that the person with mostly type 2x has their muscle fibers shortening at a faster velocity than the person with mostly type 2a if the exact same number of myosin is interacting with actin at that time? And this would come down to like theory number 4, okay, from the past. Well, if somebody with mostly type 2x fibers has myosin light chains that enable their myosin heads to actually cycle at a higher velocity or faster velocity than somebody with myosin light chains within type 2a, that would account for this problem. Because think about it. If that were the case, right, both these people would be producing the exact same amount of force. Right? So the same number of myosin and actin would be interacting with the person that has mostly type 2x compared to the person that has mostly type 2a. But the myosin heads within the person that has mostly type 2x, those myosin heads would actually be cycling at higher velocities, pulling actin towards the M line at a higher velocity. So with theory 4, you actually could have the exact same number of myosin heads interacting with actin, and yet the person with mostly type 2x fibers would be able to be shortening their muscle fibers at a faster velocity at that exact same force production because their myosin heads would actually be not cycling at a higher frequency, but cycling at higher velocities than the person with the type 2A. The sort of historical answer to this would go back to, again, well, the type 2X fibers have myosin heads that can cycle more frequently than the type 2A fibers can. So it might be true at this exact point in time, these two muscle fiber types are producing the same amount of force, but the type 2X fiber, right, can shorten actually at a faster velocity at that same force production because those myosin heads, they can actually cycle at a higher frequency. So they both have the same number of myosin heads that are interacting with actin to enable them both to produce the same amount of force, but because of the fact that in the type 2X fibers, the myosin heads can cycle more frequently at this exact same force production, these muscle fiber types have faster shortening velocities. Again, that may answer a portion of the question, but there's got to be more going on inside of the type 2X fibers than just that. And it seems quite evident that it is related to these intracellular proteins that we are going to be studying and trying to figure out for a very, very, very long time beyond today. So what I just went over with you in this lecture is probably in exercise physiology. It's really probably an area that we understand some of the least about. Like, what are all the things that account for a type 2X fiber being more powerful than a type 2A fiber? There's much, much, much more going on there than just the type 2A fiber can't shorten as fast as the type 2X fiber. Like the myosin head cycling frequency of the type 2X fiber being higher than the type 2A fiber just doesn't answer all these questions. If this stuff confused you, that's good because it confuses everybody. Anyways, in the next module, we will move on to talking about different theories related to skeletal muscle fiber fatigue, and then start talking about cardiac and smooth muscle some before we end the semester.